slab theoretical part, but that's later. For today, before they all get tremendously bored about all the theory, we will look at these are fairly very, very simple example, but I'll try to mix and match the examples with the theory part of it. Perhaps if you can turn that thing on. Any questions broadly speaking, in terms of yesterday's discussions? No. Okay. What I would like to start out, of course, one of the small disadvantages we have today while running these examples is I haven't said a whole lot about serviceability so far. I mean, I wanted to cover that. I still have a few more slides to cover, but I did not cover. I'll go back and cover after doing a few examples, you know. So we're putting the horse behind the cart for today, a little bit. But what I want to say is that I have not also covered the concept about the moment of inertia in its gross value, I gross, I cracking, and I effective. So people have to really understand that carefully before we can even talk about a design that would be checked against serviceability. You know, unfortunately, serviceability is the primary issue, primary design controlling issue here, unlike in steel, you know. And another thing, if you are dealing with tension failure, the equation to Mn is relatively simple if you are dealing with a tension failure, but it gets a little bit, not a whole lot, bit more involved if we are dealing with a compression failure. You know, that is where that equation with that square root of a thing comes into picture. So what I want to do, I mean, I know this is, for some of you, maybe this is fairly sophomoric aspect of it, but I will try to keep it as simple as I can. That is the strain compatibility. In this case, if you call it FRP, we said it is 0, 1, right? So, if the strain is let's start with the compression failure, because the tension failure stuff is extraordinarily simple. So when we say it's a tension failure, I said just now, extraordinarily simple. So when we say it is a tension failure, what are we saying? You have this is predetermined, right? If it's a tension failure, it's already predetermined, like 0.01 times modulus times of the GFRP. So that's predetermined. So this number is 0.01. Young's modulus is also predetermined in a way, or given for FRP, which is times the A of FRP. That's what I mean by predetermined. So Mn, I cannot go right in big hurry, is all jumbled up, so I'm going to write it slowly. So if this number, let's say, it's going to be given to you anyway, if this number is say 6 million psi type modulus, so this automatically becomes, as I told you yesterday, 60,000. This times this. And then this is AFRP. And then you multiply that with the D minus A over 2. This is this is A. Okay. So D minus A over 2, your neutral axis is somewhere here. This is, that's not D1. So that is the neutral axis. And we can easily find A from force equilibrium. So you see what I mean? Therefore, you do not have to solve this as a quadratic equation. That is the advantage of, you know what a lot of people do? A lot of people would even simply say, I have accurate point. That's what people do. A lot of, because we have many other factors of safety. Now it doesn't matter whether I'm talking this D minus aorta is 0.9D or 0.85D. It's going to hover around that number anyway. You follow how a designer thinks. A good designer doesn't really rely heavily on minute number crunching. He or she always looking for a farmer's approach. I'm going to spit in the air, see which direction the wind is blowing. That's a good design. So they normally, instead of going through the force equilibrium and getting this, they would simply say 0.9, 0.85. For steel, it may be 0.85, 82. For composite, it's probably 0.992, simply because of the smaller. If you really, I don't know how many of you observed it, in a tension failure, not compression failure, in a tension failure, the depth of the neutral axis at failure, uncracked part before it crushes, is about 0.8. So people say, for all practical purposes, it is about 10%, 8 to 10%. That's what the people say. From a designer point of view, mind you, remember, or else if I had to go through all the equilibrium aspects and what, I'll go to this, and then I'll substitute it in here. But from a designer, this is more than adequate. That's the thing. So there is no, my message here is, there is no quadratic equation there. Now, on the other hand, if I go to compression failure, I will get into the quadratic equation issue. How is that? So this is the lowercase c. We are saying it's a compression failure, right? Therefore, what does that mean? This is going to be 0, 0, 3 or 3, 5 or 4, depending on the code. As if Professor Prakash is saying, if I use fiber concrete, that could very well be 0.005 or 6 in that range, you see. So from that, I'm going to fix this. So this is no longer that. So the tension, the strain value in tension is going to be epsilon Cu, which is 0.003, right? That is that. Multiply that with D minus C by C, right? Then that is the compatibility. This is what we call strain compatibility. So then this is in an approximate sense so
maybe you could do the other one. The one that is
so this is AFRP times FFRP and FFRP is, this is the one. That is the strain, you multiply it with 6 or whatever, EFRP. So, if you, this should be equal to this, that is the equilibrium part of it, and you substitute, from this equilibrium, we are now trying to find C, which turns out to be a quadratic equation to find C. Once I know C, the equation for M is essentially going to be the same, except you are going to look at it from the standpoint of, whatever that 0.85. F prime C. It's not writing that.
Yeah, I think there is some, we can write, yeah, the anti-touch or something, you have to remove that. That's okay, you have to do something. Maybe you can go to the pen, yeah.
85 F prime C, that is the stress, B times A, which is beta 1 C, and that is equal to A of FRP times 0.003 times B minus C over C times E of FRP. So now with this equation, you are trying to solve for C, which is a quadratic equation. That is where you got that square root business and what have you. You follow me?
Sure.
This is a very, we learned this in, as soon as you get into structural engineering, concrete, you learn that very first thing. So that is what we had. Once you have the C value or A value, you can find the bending moment value. All right. Now, keeping that, the reason I say that is because today in our examples, very, very simple examples. Hopefully I can cover 8 or 10 today, maybe 4 or 5 tomorrow, because the ones tomorrow are more involved. The 10 are fairly rudimentary. The reason I'm even putting this here today, I'm going to use some of this in the example. That's why I even brought this up. So, I don't know why it didn't print. That is a 12-inch by, okay, this is a compression controlled section. And this is a rectangular section, 12-inch by 20-inch section with a cover of 2.5 inches. So the strength reduction factor, somebody was asking me yesterday, for compression is given right there. That is the strength reduction factor. So how do we know that this is leading to be a compression? That's the first question. How do you know? Anyway, before we go there, what we typically do as a starting point in the design of a bending member with steel reinforcement is you start with approximately 1% for beam bending with steel as the amount of steel, 1% of the cross-sectional area B times D. D is the effective value. That's just a guide, remember. It doesn't have, it could be 1.25%, it could be 0.8%, but that's for beam bending. For columns, we use approximately 2 to 3%, but we can go sometimes for high-rise building columns, we go up to 8%. On an average, that's the highest. The code clearly says don't exceed 8%. But on an average, we use more like 4 to 5%, which is still slightly higher, but you can go safely to that level. I would use 2 to 3% to begin with if it works. Another thing, in steel we like to tell the students is that make an attempt, if your design fails due to the fact that not able to satisfy the moment requirement, first thing we want them to do is increase the area of steel. The second thing is increase the strength of the concrete. So these are the immediate, don't dabble, if you can help it, of course. All these are if you can help it. Don't dabble with the cross section to start with. Try these two first. So we keep that philosophy in mind. And now, that's for steel, that 1%. For FRP, we may be talking about 2 to 3%, especially when you're talking about compression failure. If it is a tension failure, we initiate the discussion with 1.5%. Okay, if it's of course, tension failure has a penalty. We talked about it theoretically, but that is in that range. You have tension failure around 1.5, less than 2. Whereas a compression failure is about 2.5, 3%. You may get there. Okay, those are the broad parameters before you initiate a design. Okay, now there was a typographical error. That is not 7, it is 17.5. B times D. B is 12, that is 17.5. So what did I say? I want to make sure for this given cross section, we have 4 number 8 bars, and the number 8 means 1 inch diameter bar. It is 0.79 square inches area, so 0.79 times 4 is 3.16. That is the area of FRP. And the row F, the row implies that is the what percent? Here you see 1.5% of the cross-sectional area. When I say cross-sectional area, is the effective cross-sectional area, not the total area, not the cap D, but lowercase d value. Okay. Now, what is rho FB? That's why I put this thing up. How did I get this? It comes from here. Okay, that is from the compatibility issue. Strain compatibility, you're correct. And if you don't know how I derived that, it's all in there if you look at it, but I'll be very happy to provide you with additional intermediate steps if you, but this comes from the strain compatibility. Okay, that's a very, very important thing because that determines whether a given section is in compression or tension failure. So in this case, as you can see, rho FB is 0.01, whereas we have provided 0.15. Obviously, it is a compression failure. So that is the first step one must arrive at. Is that clear? So if it is a compression failure, we are talking about 0.65. Tension failure, it is 0.55. So when I say it is a compression failure, that's why I went to the black, whatever your green board there, and now I'm trying to find the stress in the FRP rebar. And that equation, you have that equation. I gave you that equation in your earlier slides, and you substitute it in there. And I said this before, I'll repeat it. This component is negligible, really, compared to this component of that equation. So really, you can get away, that is what? That is 324 divided by 4, that's 81, and this is a much higher value than that, so you can neglect that pretty much. If you do, again, if you don't know how I arrived at it, I described how to arrive at it. If you don't know it, please let me know. So we found the stress under the compression mode of failure, which is a function of 0.003, and as Dr. Prakash was talking about, if this number ECU is 0.4 or 5, 004, 0.006 or whatever, then obviously this is going to shoot up. So that is the advantage you have by having a higher strain to failure in compression. At any rate, so the A value, where is this coming from? This is strictly coming from equilibrium equation. ASFF is the force on the tension side, 0.85 F prime CBA is the force on the compression side. Therefore, we got a value. A is different from C. So the neutral axis, from American code point of view, this is the neutral axis depth, whereas A for a rectangular equivalent idealized rectangular stress block point of view, A is beta 1 C, whereas beta 1, I told you, varies depending on the strength of the material. The reason they cut off in ACI at 8,000, and they said above that it is still 0.65, because for some reason we feel 8,000 is a cutoff limit for regular concrete versus high strength concrete. So the code here, I didn't mention that emphatically, is only valid for regular concrete. Code is not calling for higher strength concrete. But I really like this concept about increasing the strain value using fiber. Yeah, that will help a lot from an economics point of view. But maybe you know better than I do. Why it didn't catch on, the fiber concrete in US, I do not know. But very few people, as a structural concrete, we do that fiber concrete all the time for basements, for sidewalks, for driveways, we do that all that. But it never caught on. My very good friend, Suru Shah, worked his whole life on that. One of these days, I can't resist with asking, why the hell you didn't get this going anywhere? I don't know why, do you know?
Now, I think the major issue is, to get really steel-free concrete, you end up putting high volume dosage fibers. When you want to put like upwards of 1.5, 2%, the mixing becomes.
So it doesn't exfoliate.
Yeah. Balling effect.
Okay.
On top of that, again, anyway you will end up putting some steel regions because here you are dispersing the entire medium. So it helps in ductility, but in steel you are lumping everything at the location where you want in tension. So you end up with more economical sections when you have regular.
So you use, when you say fiber here in this country, you use mostly steel fiber?
Steel?
We normally don't use steel fibers. We only use polypropylene, polyethylene type fibers.
There are two varieties. There is a microfiber, which we use for shrinkage, which are typically less than 0.2 millimeter, the short fibers. And then we have macrofibers, which are typically more than 0.2 millimeter in diameter, longer. So the synthetic fibers about last macro synthetic fibers, which are structural for structural crack, they are available for last, I would say, 5 years, 10 years. So now increasingly being used in India. They are more flexible, malleable, so you can mix it very well in concrete. But the efficiency of crack arresting is less because the stiffness is less. So now people are using both steel as well as this. Again, steel also now again microfibers are available, which are again easy to mix in special concrete. But again the cost, for example slab on grade, as you said correctly, here also a lot of industrial flooring they do with steel and synthetic fibers, but they are, I don't know, somehow still there are a lot of resistance.
Yeah, it didn't catch on. There's a huge amount of funding given for 20 years in US, but it just didn't, structurally nobody is really using it, to be honest. On grade, yes, they're using it, no doubt. But structurally, not able to. I really need to know why. But another important thing is the sizing issue. You see, people, what happens is industry guys take it onto themselves, don't fully understand the science, and then they want to use it. The balling effect comes because there is no appropriate sizing on the fibers. If you have this sizing, it can exfoliate much easier. The dispersion becomes more uniform. So maybe that is another area that one needs to be working on, But that definitely has a lot of potential. If Bazant worked on that from a theoretical point of view, and Suru Shah did that from experimental point of view. Okay, but that's where we are on the microfiber type thing. Okay, so once we know, you understand the A comes from the equilibrium, and now it doesn't matter whether the nominal value is obtained with a force function from the tension side or the compression side, because they're both are equal. AFFF is equal to that, so it makes no difference. So that is this is the nominal moment, we call it. Now I'm talking, analysis part is pretty much over. Now I'm going to talk about how we compare it as a designer. So Mn is the nominal moment, phi is the reduction factor from the material point of view and also from the point of the failure mode. That's the phi value. So your ultimate moment, including the load factor. So in my next day or two, when I say load factor, load related moment, we call it, implying that that includes your load factor. So keep your, that slide where I gave you on the load combination, keep that slide in mind or keep it open because we will be using that. So the message here is the following, that this number should be higher than M sub U with the load factors. That's about all is there with reference to bending design in a compression mode. So any questions now? Anything on that? So I don't see. But the tension mode of failure I'll be talking about in the next example is much, much simpler because you don't have to even worry about that quadratic equation type thing. If it is a tension control, all I have done was I took the same cross section and I reduced number 8 bar down to number 5 bar. Say, so that the thought process would be streamlined, focused on area of steel rather than something else. So if you look at it, again the same drill, right? No big deal. So you have 17.5, the rho F is 1.24, so the number 5 bar is 0.6, 0.3 I mean, so you get that 1.24, 4 times 0.31. Anyway, the rho F is as given the equation, we gave you the equation, again coming from that compatibility, and you can see less than 1.
1.4.
Right. That's what it is. Therefore, the phi factor is 0.55. So you, yeah. So this is how we dumb it down. So these are very rudimentary examples. When I go to the design of a two-way slab, you will see the complexities, That's why I kept it to the last. I'll take a couple of hours to run the whole example. It has many, many steps and many, many slides with it. Okay. All right. So we talked about, is that clear? What is a compression control? What is a tension control? Okay. So what are we learning here? Phi factor is different, number 1. And the rho versus rho F, rho higher than rho F is compression, rho less than rho F, tension. So now all we are showing you there is how to find the phi times Mn. Okay. You can see that is Mn, multiply that with the phi, that is in inch cubes. And the C for the balance is given to you there. It's a very standard equation. This is the force, AF, FFU is the force, that is the lever arm. So A over 2, what is A? 0.85 times C. So, okay, the difference in terms of tension control and the compression control, I told you that yesterday, I don't know how much you caught on to it, is the minimum value of reinforcement. That is if you're going to design it as a tension failure system, you must, why that is given there. Where that is coming from. You may not know how to derive that equation. You know where it's coming from? It is coming from, we equate the first crack moment that must be resisted by the reinforcement. And that's how we arrive at that minimum, so that when it has a very first crack, it's not going to have a catastrophic failure. It will be held on together before it meaning the crack opens up. That is my emphasis. This is a B sub W. That means whatever the effective width or whatever, even for the T sections and so on. So at any rate, the AF min is 0.96. So if you remember in the same example in the previous slide, we provided 1.24. So we are satisfied. We have satisfied the minimum requirement. Okay, here, there it is, 1.24. So this is an extra check compared to the compression failure.
In this case, that 5 mn, that must be equal to ultimate moment or
ultimate, okay.
Ultimate moment.
This, please note, this moment, phi times mn, must be always higher.
Higher than
M sub u.
Then
That M sub u is, you will see that when I run I call this an analysis problem. You will see that in a design problem, that M sub u is inclusive of your load factors. Not only that, you have to go through combination 1, combination 2, combination 3, 4, 5. That's why you keep that chart in your mind. So anyway, the straight answer to your question is phi mn should be larger than M sub u of different load combinations, inclusive of the load factors. That is the answer to your question. I'm trying to look what slide number I have that. It's, I think, 105 or something like that. But at any rate, I told you, I alerted you several times that you need to keep that slide in your mind. What slide number? That slide?
96.
96, okay. So that slide number 96,
yes.
oh, you opened it. Okay, thank you. So you can see, I want to keep repeating that. That's slide number 96. So we have to check for all these load combinations. 1.4, only dead load. So you see, the reason I want to thank you for opening it, I'm glad you opened it. The reason I want to go there is, why is it that it is 1.4 load factor when only dead load, 1.2 load factor when it is a combination of dead and other loads? Again, this is where what they call uncertainty of loads acting on a structure would come into the play. That is where all these concepts come into play. You see? And many dissertations were done. All this comes from field evaluation. So they go to 1,000 different slab systems, for example, and measure what is the thickness, and you say, okay, the max thickness value is 40% higher than the called for. 6-inch means sometimes people put 8 inches, sometimes they put 5 inches. That is that bell-shaped curve. So that is where the factors were derived. Again, we have no control on this, I said. This is, we have two sides of the equation, right? One is the resistance side, which we talked about so far. The other is the load side. This comes from the load side of the equation. We cannot touch it. It comes from the ASCE 7 which calls for these kinds of load combos. Likewise, you have a lower live load, dead load combined with live load, and you can see, because the uncertainty of live load is more than the dead load, that's why the factor is higher. So
in Indian code we have 1.5 dead load and 1.5 live load. Both are same
yeah,
in Indian.
yeah. I don't agree with
The
that.
uncertainty
Is higher
both
with
in
live load. That's why we did this. So that's why I said I don't necessarily agree with the. I have a tendency to speak my mind. I get into trouble, right? So, but that's what it is. Other load combinations, you can see how. Again, I'm not going to get into it because we have no control on that side of the equation. They are given to you. You don't believe it. It looks so simple. ASCE 7 on loads and load combination is this thick a book. It's about 1,200 pages. So that tells you how much work goes into it. Therefore, I'm very cautious not be too critical about it because there's a lot of thinking went into it. You see, it's easy for me to stand here and criticize it, right? But you don't understand the other flip side of this coin where how much work went into it, Nobody takes it casually when they make a statement. So those are the kinds of checks and balances we need to make. Okay, let's get back to our okay. So, couple of things. We only talked about strength limit state. This is all a strength limit state. We didn't say a word about stiffness or other kinds of limit states. You remember the 4 limit states I gave you? So that needs to be checked, but I'm focusing only on strength for the time being, So that gives you a good check. One-way slab design. This is another example. So, I'm sure most of you know what is a one-way slab versus a two-way slab design, and you see there is a lot of fascination to arrive at these slab related moments in a most high accurate manner and all that good stuff, right? Mathematically sounds good, but a designer doesn't care. Therefore, what I'm trying to say is, first thing you should recognize, there is a positive moment, meaning causing tension at the bottom, and a negative moment causing tension at the top. That's positive, negative, it's a definition, right? That's why I said tension causing at the bottom and the top. So how do you recognize that? If you draw a bending moment diagram, you will see that. As the first thing you appreciate. The second thing you should appreciate is right off the bat that approximately what they call positive moment is WL square over 16 or 17. The negative moment is WL square over 11. You know what I mean? So that is the second thing you need to recognize. And then now you're ready to design for the positive moment and negative moment. So anyway, that is how they simplified it. So we are now going to design this for both. Another interesting thing they talk about is your positive moments are lower in the interior spans compared to the exterior span. Again, people quibble about all these kinds of things. Ultimately, they don't matter much, really speaking. But we have to go through the motions anyway. That's what the code is calling for. But our code says, I don't know what your code says, WL square over 11 for the max negative, WL square over 17 for the max positive moments. That's an oversimplified approach. Remember that. Those are the words, oversimplified. But that works. As long as it works within a few percentage points of view, it doesn't matter, you know. All right, now, so where do we start? Again, as I indicated, for a beam, we are talking about L over 12 or something. For a slab, we are talking approximately around, this is where we start. I'm not saying that works. That we're going to start with that and cross-check whether it is working or not working. That's our next step. So this is all given, the F prime C, that is about 25 or 28 or whatever, 30 MPa. And this is given again, 90,000 PSI. It may be different, you know. I'm taking that as a pretty standard value. No.
Quick question. Sorry.
Sure.
Typically, you know, the L by D ratios that what we use for steel is on the higher side. Probably, I think, because this is governed by
Exactly. That is the key point. You see, the L by D ratios for steel are going to be higher than the FRP. That's because of deflection. I want to keep emphasizing. I didn't go into the deflection part of it. I will show you that a little bit because those are on the subsequent slides in my theory. But what I want to say is, I told you many times already, the deflection controls, but the important message is that deflection we are talking about, like say PL cube over 4080, that I value is the effective, I effective, not I cracking, not I gross. That is the message I want to convey. Yeah, and that is the reason why we have a higher L over D type for steel.
I'm just adding on this.
Sure, please do, please.
You know, that addition of discrete fibers, I said, either synthetic or steel, greatly helps in improving your flexural rigidity.
Right.
Then you can cut down the rebar, then the design becomes more economical.
Exactly. That plus, from a fatigue point of view, it's a great help. That is why I never understood why it did not take off. I don't know why. I mean, if I were doing it, you know, I nearly need to tease Suru Shah. What the hell, you got 20 years of funding, what happened? You know, I don't know. I'm serious when I say I don't know what the reason, but it has a lot of advantages. So, but anyway, so you see right away how inaccurate potentially the approximation is. What did we do? I said L over 17 or 16, I got 13.4. I'm trying out 12-inch thickness. May work, may not work, that we will know in my next step. But that's what we did. So here is this slab, self-weight, and there is no superimposed dead load. Now I'm going to answer, okay, here. Here I said 11 and 17, if you remember. So it depends on the two-way slab or a one-way slab. In this case, they are taking 14 and 10. Again, that is up to your code. Our code clearly defines this. That's my point.
So
Okay.
we also have a code coefficient that gives you on a table what should be the value that it should be.
Yeah, we have that same thing. The code I gave you, American 44011, defines those numbers. Now, I'm trying to add Dr. Chan's question here. Please look at this. 1.2 times the dead load, 1.6 times the live load, and that is the live load moment. This is the MU that must be lower than the phi times MN. That is the design approach. If this mu is not lower than the mn times phi, I keep calling phi mn, then the design did not work. But if phi mn is higher than this, it worked. So this is where, this is only one check. This is only one check on that table we just showed you. There are 6 other checks here to make only in the strength aspect. Likewise, you have 3 other checks in the serviceability aspect. There are a couple of other checks for extreme events and for fracture and fatigue. So this is an involved process. If you don't have fracture fatigue issue, you don't have to check for it. But you must check for both strength and serviceability. I know some of you know some of this. I'm also trying to convey a message, especially to the manufacturers, you know. So they need to be aware of this, and they should be equally aware in promoting the FRP by suggesting some of the ideas like this fiber concrete, you know, which would help a lot. Those are the kinds of, if you have any discussion, please let me know. We would discuss it. So what's our goal? Our goal is to find the magnitude of FRP, assuming this is a tension control. So here is the clear cover. So what does that mean? FFU, let me go back. You see, FFU star is 90,000. FFU is the factor 0.8 or 0.85, the CE factor. In this case, we use 0.8, but you can use 0.85. Different codes are using different facts. But the message is FFU is the one, our design controlling factor for the design. See, right away, I like to emphasize the average value, the average value of this is what? About 25% higher. Like you're talking about 110 in that range. And we reduced it -3 sigma. And that is what this number is. So keep it in mind, your average is not what it is. So my message is, I have 110 KSI FRP, while in fact, I am using 72 KSI as my design value. So right away, you almost have a 50% reduction. You see, that's only one factor. We have load factor, therefore we have a 1.6 or whatever that. You see? So when you add up all these factors of safety, it comes to 5, 6, 7, 8. You know, in that's what happens. It's what happens. You know.
Sir, you told to check the different load combination cases. Even if the bar is being used in zone 2 sections, there too we will have to check the seismic load combination? No,
the load combinations are static values. The earthquake type things you are talking about are the dynamics. Only for the earthquake part, this you have to check. There's no way out. That has to be checked. But the way you go about checking for level 1, 2, 3, 4, 5, 6 is different. That is either a pseudo-static or equivalent static or a first mode, first fundamental frequency based. The analysis gets complicated from 1 to 2 to 3, you know, whatever that is. Right. But what they are saying is, maybe this is your question, what there's for low levels of earthquake, which is say category 1,
yes,
we are allowing you, permitting you to check in whichever the way you want to check, with FRP. But you go to category 2 or 3 or 4, we are not guaranteeing how FRP works. Therefore, code is not giving you any direction of how to design for level 2, 3, 4, 5, 6. That is the clarity. Okay, so if you assume a tension control, you don't have to. That's entirely up to you as a designer. Then there's a clear cover, and F sub FU we already determined. So if my D value is 12 inches is the total depth, and you subtract the clear cover as well as half of the diameter of the rebar. So that gives you cover, not clear cover, that one in the parentheses, 0.75 plus 0.625 over 2, that is called cover. 0.75 is the clear cover. Sometimes the terminology is also, not simple. Okay. So again, from the stain compatibility, that equation coming straight from that one on that green board. The C value is 2.2 inches, and M being a tension control, that's what we are talking about. Again, the phi factor, please note here, MU is phi times MN. Exactly. So phi, if it is tension control, 0.55, then this is the amount of area required. I know my M sub U because the previous thing from a design, at least for one check of those 5 or 6, that's what M sub U I know, and that is a tension control thing I know. Therefore, I am substituting all those. B1 is what is B1? If it's a 4,000 psi count, beta 1 is 0.85. If it's a 6,000 psi, beta 1 is 0.75.
Yes.
Like that. So FU, we already talked about it, 72 KSI. That is FU. So anyway, from there, that is what we got. What we need is 0.26 inch square per foot width of your slab is the amount of reinforcement needed. Okay. Again, we checked for rho F min. It is very, very important all the time. This is the rho F, AF over BD. There is a limit. This has to be bounded between 0014 and 0036. There are reasons for that. That's a code requirement, not mine. And you can see. So what we need as a minimum is 0.52 inch square compared to what we got based on the load. Therefore, this is what controls. And number 5 bar is what, 0.3 square inches or something like that. 7 inches. So 0.52, 0.3 divided by 0.52 times 12, that is a selection, comes out to be roughly 7 inch centers. You see how, I suppose, the reason I'm explaining, I don't need to explain for structural engineers. For non-structural engineers, I need to explain how we got from here to here, okay? Corresponding to this. So it is the area of number 5 is 0.3. That divided by 0.5, where are we?
0.5.
Yeah, 5.2 times 12. Okay. All right. So do you see how we arrived at it? For a one-way slab, a two-way slab is much more in tension. A two-way slab is much more difficult. So now what we are asking is verify these assumptions. So we have placed 0.53 amount. If you look at it at the back, we have, instead of this gives you 0.53, even though we only need 0.52. So that is what we are trying to. So we are making a check. So first we want to make sure it is tension controlled or not. That's what we did based on the balanced approach, which we talked first thing in the morning today. So these are some of the notes. For positive moment, we concluded we need 6 foot grips per foot. Then the minimum GFRP, number 5 bar at 7 inch. Slab design must be checked for shear, crack control, creep rupture limit, and deflection. So I haven't done that yet. I will do that as next step or later. Not an efficient design, because the slab thickness can be lowered to satisfy crack at this service load. Remember, what did I say? You dabble, if it is not an efficient design, you can reduce or increase, in this case increase, the amount of GFRP. Then reduce the slab thickness, so you have a less self-weight. That is how you need to think as a designer.
Why we are not adopting the compression control in this case?
No, this is just an example. That's all. I'm trying to illustrate a point. No. Definitely, if I were a designer, actual structure, I'll be using a compression control. Yeah. But here, remember, we have to check for 2 things, right? Bending moment on the tension side and the compression side. The tension side is between the beams, the compression side of the moment, which is WL square over 10, over the beams. Okay. So redesign for cracked slabs at service. So GFRP slab for flexural service strength is, so that is per the code, 0.2. That's the key point. All the others is mechanics, you can do it, but that is the key issue. The thumb rule is designed for flexural strength, that is twice the ultimate moment. And typically, like I said, we assume for compression control 1.5 to 2%. No, don't exceed more, I'm sorry, I didn't say it right. 1.5 to 2 factor of row balanced, So don't exceed more than that. 1.5 is a good number times the balanced value. So we already found the balanced value in the earlier slide, 0.008, and we are saying for a compression control it is 0.12. From there, again, as soon as you talk of compression control, you have to use that quadratic equation. And my feeling is, I haven't thought through enough, but I can bet you, this can be, first of all, I said we can throw this term out. That's first, But second of all, I really believe even this can be reduced and removed from the root and use a lump sum factor that will give you an answer. That's neither here nor there. I'm just saying how one needs to think through as a designer, not as a mathematician. So for compression control, you see, we are talking about, we still have a lot of reserve. If it's a compression control, our strain, the stress is only 57.5 KSI. It could be 72, you remember that? Yes. So we still have 25% waste. But that's okay. That's where you need to balance this out, as much, push it as much as you can by, you remember I told you a few minutes ago, by reducing the depth of the concrete or whatever. Of course, you can only do it so much. Okay, here. So we're selecting 8-inch thick slab as opposed to 12-inch thick slab when we did the tension control. That is the point, isn't it? So now suddenly we reduced a good bit amount of, you keep asking me about earthquake design. You know the first thing people worry in earthquake design? How much can I reduce the top heaviness of any structure? The dead load, we want to minimize that. So this is an excellent example.
In fact, in a building, the majority of the dead load comes from slab.
That's right.
Optimize the thickness, you reduce the demand.
And that I'll extend that statement. As the building goes up, like say 10 stories, 20 stories, 40 stories, say, it is essentially the dead load that controls the design, not the live load.
Yes.
In bridges, let me tell you, if I have a 100-foot span bridge, my dead load effects of say 25-30%, say call it 30, the live load effect will be 70%. I extend that argument from 100-foot span bridge to 6,000-foot span bridge. The dead load is 90% and the live load effects are only 10%. The same argument goes, especially so for earthquake type systems. So as a designer, you need to keep some of these in mind so you can, see here is a great example. We reduced it from 12 to 8 inches. Very simple, very rudimentary. You can't get an example simpler than this. You know, as a designer, there are many other complexities. I didn't even introduce any of them. But for the simplest possible, you can see. Now we are going to talk about your negative moment QL square, WL square over 10, positive moment WL square over 17 or 14 in this case. So L, the effective span length is 18 feet, and the M sub U has the phi factor, and here is another simplification of all that. So what did we find? All you need is an effective depth of 5.7 inches. So if somebody is very critical, they can reduce it to from 8 inches to even 7 inches and still get away with 5.7 inch effective depth, total depth of 7 inches. So that is how, it is not just the savings in the materials, which is minimal, it is the overall efficiency of the design. The self-weight. Yeah. So, modified factor for 7-inch thick slab. So we went back and reiterated that. So we did a similar kind of a thing, went through the, but now I want to talk a little bit about temperature and shrinkage reinforcement. I don't know what your code says. Our code is saying it should be the rho factor for shrinkage and temperature is 0.0014 as a minimum times BD. You know, the effective times.
Here it is 0012 for steel.
Okay.
But we don't have a code for FRP, probably slightly higher.
Yeah.
In GFI.
Yeah.
In RCP it is written as 0.001.
In my opinion, assuming 0012 or 1 is okay, it should be lower than that because the coefficient of expansion is much lower in FRP than in steel. Okay?
So actually, most of this shrinkage problem what we are finding is, yes, as in temperature effects are less. Mostly, you know, at least in Indian context, you know, they use higher water symmetry ratio.
No.
That tends to be the major.
The shrinkage issue.
Yeah, shrinkage.
That's right.
More fibers.
That, you see, I don't know you were here when I was saying, when we were pouring concrete with reference to the McKinley wheel bridge, our regs are very, very stringent. So the guy, the ready mix guy did not meet the standard. He had to dump some 20, 30 cubic yards of concrete. Now, talking about your statement, we do not allow more than 0.35 as the water cement ratio. Maybe even a little bit less. That is correlated to the slump. We do not allow vibration more than, say, 20 seconds, actually 16 to 20. If it goes more than that, you know what happens? There is a separation or segregation of fines from the coarse. Okay. We want the vibration to be spaced at 20 inches. We even have a definition of RPM. So when I say 16 seconds, of what RPM am I talking about? So it's all related. So we are not stringent about it. And I've seen concretes here, they easily have, on an average, I dare say, 0.55 to 0.6 here. 0.5 to 0.6 is the water cement ratio in India. At least the ones I saw. It should be.
But now it has come down.
Come down. Okay,
with
good.
all the advent of super plasticizers.
Uh-huh.
But at least in the contractors who are big contractors, they don't go anything more than 0.4.
Okay.
And
Good.
But at the lower level, the small residential construction is being still done by people.
Workability is the dominant factor there.
Yeah, that's the major. That's where they tend to add water because super plastics are costly. The strength is not really a big governing factor in residential construction. Concrete strength.
We are using super plasticizer rather heavily and effectively in terms of geopolymer concretes. You see, we don't use any water. In geopolymer concrete, zero water. 70% of fly ash. And the only way you get the workability is by using the super plasticizer. See, have you done a geopolymer concrete in the country today? No.
She's we have a lot of work, I think.
No, I mean in the construction, I meant. I know, it's in the...
Precast plants they're doing.
They are? Oh, good.
Yeah, but not really the full-fledged, we cannot deliver, order a concrete from RMC who will deliver a geopolymer.
So what type of curing you are adopting for geopolymer?
We are not adopting any curing other than your ambient, that's it. We built what? 150,000 square feet plant to prefab the modules. 125 or 150, I forget, but it's in that range. Yeah, we are not doing anything other than, and we are attaining about 80% of the strength within a day. Roughly 75, 80%, within one day, I mean. Yeah. I think the super plasticizers help, and the proportion of some of the other admixtures are helping us too. So it is quite a bit dependent on two things: the local quality of fly ash. Oh, that's a killer. That's a killer. And the second one is, remember, don't ever use geopolymer concrete without certain amount of aggregate. You may get the strength, but creep is a killer. If you do not have adequate amount of concrete, it can creep like crazy. Yeah, so it can. We never got without coarse aggregate of certain range. We normally don't go beyond ½ inch for geopolymer concrete. We even proportion the coarse aggregate. That's another stringent requirement for us, like 3/4 or ½ inch. But here geopolymer, we only go max ½ inch. Without it, believe it or not, we didn't get a modulus more than 1 MSI, like 6, 7 GPA. So much so, what it did is creep load primarily under the self-weight has resulted in slow but steady increase in crack growth. By the time we realized it, it's too late. It looks good on the first day or 2 days. Once you go beyond that, you'll begin to see the cracking. So that's why I asked you, are you people getting into high-level construction? Not in the labs. I know actually a very good bit amount of work was done here in these countries. Like Singapore did a lot of excellent work from you all. There's somebody here from Karnataka, did I forget his name? I followed some of his papers. They did some good work.
Our colleague Professor Subramaniam has done a lot of work. But mostly, as you said correctly, now they're looking at blocks and small elements which can be done with precast. And handling that alkalis, that is a major issue still that need to be resolved.
Right. So that's where we are on that. So sorry for digression, but at any rate, that is the spacing we got based on. You even modified it from 8 inches to 7 inches, you see? So you can see how we take advantage of. Now, this is the most important thing when it comes to GFRP. What is most important? Crack. Why is it so important? Because of low modulus of FRP. So again, these are empirical values given to you there in terms of this check when I said empirical value. So keep that in mind. So here CE is 0.8 or 0.85. I will leave that to you depending on your code. And this is a beam, and this MU is inclusive of your load factors. So we need, whatever we're going to do now, we should make sure that the MU or M phi times Mn is higher than Mu. That's the idea behind it. So here, the most important thing to keep in mind is the service load moment, not the ultimate load moment. Means what? We don't have to worry about the MU part of it, like 1.4 dead load or 1.2, 1.6, those kinds of things. That's why that tabular form is very important. Keep that in mind. Whatever the crack width controls we are talking about, do not account for load factors like we do in terms of MU. Okay, so you can go through that. The max crack width they're suggesting is 0.028. For our bridge decks, the crack width is around 1/3 of that for our bridge decks. That's steel based, but we can relax that. When you talk of stringent quality control related issues, the reason we have such small crack width limit state because the de-icing chemicals go through and lead to corrosion, and that's what we're trying to minimize. And also we increase the cover from 1 inch to 1.5. Today our cover on the top is 2.5 inches. That's for bridges, not for buildings. Okay, so We can go through that. We select the 4 of number 7 bars. We're going to make some of these checks in terms of the crack width, and the equations I told you are given right there, section 7.31, and this is the equation. So you can see, once again, we are talking about the elastic analysis. We are talking about service load. Means what? We are only looking at I effective, not I cracking. So again, the D value, the effective value for this beam is given to you there, and the modulus. We have 2 equations to establish the modulus of a concrete based on F prime C. This is an easier equation, F prime C times 57, slightly inaccurate than the other equation. I gave you that other equation if you recall, but this is a little bit easier to compute, and the elastic crack analysis where we found the K value. I'll show you that in a minute. NF is the modular ratio, that is the stiffness of FRP over stiffness of concrete.
Generally, the cracks occur at the contact area of concrete and bar.
No, not at all. It should not. Then you lost the game. It is, like I said many times, crack, no matter what you do, concrete cracks due to shrinkage, for example. Yeah, exactly. It's a tension crack, so you are talking about 300 psi or 400 psi to tension failure. Naturally, concrete would crack.
Under service codes also, we allow cracking, but we limit the crack.
That's right. So
what is the minimum limit for the crack?
That's what I gave you. 0.028. There we go.
Maximum crack.
That tailor
Yeah.
multiplied by inches, how much it's cracked, and
Yeah.
The crack at
half a
half should
millimeter,
propagate to the
half a millimeter also. Because here it is higher.
1.5.
It's not going to curve right. So the maximum allowable crack width, 0.028 in
That is what we gave, and that is FRPs can tolerate a little bit more cracking with crack width. I mean, because of non-corrosiveness. Like I told you a minute ago, for bridge deck, that number is 0.01, 1/3. So that is a typical number. Talking about a minimum crack, we love to see 0 crack, right? That's as minimum as you can get. So the K value, you can see under service loads, you have a K value of 0.14 times D. KD is, say if it is 20-inch deep beam, about 3 inches is the uncracked part. Typically, if you remember yesterday we talked about, they are using 0.16. In this case, we got 0.14, but they're normally using, that's for service load. For failure load, it's about 8%. And an average number is the I effective, means the I value cracked section under service load is about 1/4, 1/5 of I gross value, and the I crack value is about 1/10, 1/12 of. These are broad numbers again for the designers. That's a good guide, So that is why we keep emphasizing the service level stress. That's the key. So if you look at the I cracked value, I don't recall the IG value. This is typically about 1/10 or 1/12 of your I gross value. I don't know that I have that here or not, readily available or not, but that's about what it is, you know. So you can kind of figure it out, 112 BD cube. So that'll give you whatever the number you're looking for. So this is the stress of the cracked section. For elastic cracked sectional analysis, we found the K and KD values. K is 0.14 and KD is 0.14 times 21.56. So that is approximately 3 inches. That's the limit check. I already gave you that equation. I really do not know where they got that equation from, I admit, but that's the equation. And the bond coefficient based on the depth is 1.4. Again, that is an empirical number. So what we figured out is, from all this, that this check did not satisfy the limit state. Therefore, we're going to continue to check the bar spacing for different purposes. The S max equation, again, that's an empirical equation, and that satisfied it. So these are the empirical checks. From the code, I identified the equations for the empirical checks.